the interesting thing is, here I show you then why you get limit point. If you have a string-stiffened shell, it turns out that the first post-buckling coefficient A is 0. Then, what remains from that first equation, right? Here is the first equation. If A is 0, I call this now rho sub s. You get rho sub s is 1 plus b times c squared here. And that is in the rho c plane, the equation of a parabola. Right? And whether the parabola opens upward or downward depends on the sign of b. If b is negative, it opens downward. And the shell is imperfection sensitive, because if you now input an imperfection, depending whether the imperfection has a positive sign or a negative sign, you get a curve that goes like this, and the limit point is always less than the bifurcation point. And notice this is symmetric bifurcation, because it doesn't matter whether the imperfection is positive or negative. If it is negative, you get a curve over here. Same result. Okay, if you now have B, and you have that formula here, you can also generate curves which kind of depict how big a decrease you get as you increase the amplitude of the initial imperfection. The shape of it is a buckling mode, right? And notice you get a curve which goes down like this, and if you now say I have an initial imperfection in the shape of the buckling mode, its amplitude is 5% of the wall thickness. You come up and you read off, and the knockdown factor is 93%. So all these are in this deco. You can get it. Now, let us then talk a little bit about solution procedures. There is a big difference whether you have isotropic or orthotropic shells, or whether you have fully anisotropic shells. What is the main difference? Now, I have here written the Donnell type equations for orthotropic shells. I shall show on the next slide what these operators are. They are linear operators, and on the right hand side there is a nonlinear operator. The comma followed by xx partial derivative, w is radial displacement, positive inward, f is the Airy stress function. We look at the operators. The linear operators remind us of the biharmonic operator, right? A number 4 with respect to x, other number 2 with respect to x, 2 with respect to y, another 4 with respect to y. As a matter of fact, if you have isotropic shell, all the q's are 0. hxx dxx is 1, hxy dxy is 2, hyy dyy is 1, and both LH and LD reduce to biharmonic operators, well-known von Karman-Donnell equations. And the nonlinear operator is defined here, always involves derivatives in a certain combination. Now, if you now go to anisotropic shell, in principle, the nice thing is you can write the equations exactly in the same form. The only thing that changes is the left-hand side, where you have the linear operators. Instead of having LH, LQ, and LD, you have LA star, B star, and D star, still written in terms of W and F. What are those operators like is shown on the next slide. And if you remember now what the HQ, etc. was, and you compare, you notice this term was also there. LH, you had HXX, that's prima. You didn't have this one. And these are the ones that are causing trouble, because they have odd number of derivatives. 1 with respect to x, 3 with respect to y, 3 with respect to x, 1 with respect to y. Why does it cause trouble? Because if you try to separate variables in terms of trigonometric functions, if you take even number of derivatives, you always get back to trigonometric functions. If you take odd derivative, odd number, you will get, if you started with sine, you get cosine. If you started with cosine, you get sine. And the separation of variable doesn't work as simple. It still can be done, but more work. Now, I'm pointing now here out how I did the level 1 solutions. For orthotropic shells, it is based on this assumption. As I said, separation of variable is possible. What are the unknowns? Xi, the amplitude, m, the number of half waves in the axial direction, n, number of full waves in the circumferential direction. For anisotropic shell, it won't work. Now, there are ways of, one way is just adding here also with cosine. That is not so nice. I found this form more pleasing, at least pleased me more. It's not my invention. It is from a gentleman with the name of Cott, who used to be chief scientist at the Wright-Patterson Flight Dynamics Lab from the Air Force. He, to my knowledge, was the first to propose this in 1970. And notice what he has done. He introduced, everything up to here is the same, but now here he introduced minus tau sub k times x. And this is a so-called skewedness parameter. You can show that this is a real number. And this expresses actually because of, due to those terms that were sitting there that I pointed out to you, what you get is a torsion bending coupling. You compress the shell, and if A16 and A26 are not 0, the buckling pattern is not going to be straight but skewed by a certain amount. And the tangent of this number here gives you what is the arctangent, sorry, of that number gives you the angle. Okay, now, if you take Cott's assumption, you substitute it in the Donald type equations, you can reduce it to this very simple algebraic equation for the eigenvalue lambda cap. I will show on the next slide how lambda is defined. Notice here I have internal pressure normalized. I will show it on the next slide how it is normalized. And essentially, lambda cap is an eigenvalue that is defined like this. What is this term here? If you have a cylindrical shell, if you have internal pressure, it must be closed. You put axial load on it, the internal pressure will carry a part of it. And this is that part. There are all kinds of parameters here that you may or may not have seen. They are all given on the next slide. These are wave number parameters, and these here are combinations of wave numbers and the stiffness coefficients of the shell. The notation was defined by Cott. Now, what is alpha m squared? Let us look at it. Here is the number of half waves in the axial direction, pi, this is the length. Here is tau sub k, Cott's parameter, n, number of full waves in the circumferential direction divided by radius squared. R is the radius, h is the thickness. C is a parameter that always bothers you in shell theory, 3 times 1 minus nu squared. For composite shells, obviously you have to choose a reference radius, a reference thickness, a reference Poisson's ratio. Notice alpha sub p is practically the same as here, except instead of plus, it has a minus. Notice also if tau sub k is 0, orthotropic shell, then this here is identical to that. It is only different if tau sub k is non-zero. This is the circumferential wave number, n number of number of full waves in the circumferential direction, 1 over r. I promise you to show how lambda is defined. Sigma is the applied stress on the compressive stress. Sigma classical is the critical stress that you will find in books like Timoshenko, okay, derived around 1910. P sub I bar is a normalized internal pressure. P sub I is the internal pressure in PSI, and it is not normalized by sigma classical, which you could have done. It is normalized sigma classical times h over r. You might ask, why is it done that way? Because I'm referring always to classics, papers that have been published long before I started this work, and this was the way that Hutchinson in a paper in 1965 normalize his internal pressure, so I just use it. It is also convenient. It reduces the equations nice.